Good evening. Welcome back. Tonight, we're on the ground, specifically on the dry floor of a seasonal riverbed in East Africa at 2 in the morning. The water that carved this channel is months away. What's left is alluvial sand, smooth quartz pebbles, fractured clay, and a dry, clean air carrying the faint scent of acacia resin and sun-baked silt. Take a slow breath. Let your body settle. We're going very small tonight. At 2 in the morning, the riverbed has shed its daytime heat. The temperature has dropped steadily since sunset, and the landscape is entering a phase of genuine atmospheric stillness. No wind, no running water. The only movement is the slow, localized convection of warm air rising from the cooling gravel, a gentle thermal conversation between the earth and the sky that won't fully resolve until just before dawn. The visual field is deep contrast and shadow. The low scrub and overhanging bank trees cast long silhouettes across the pale river sand under the faint, diffuse glow of the Milky Way. Nothing artificial reaches here. The landscape operates at its own frequency, ancient, self-regulating, unhurried. Hidden within the fractured clay of the bank, moving with deliberate, low-frequency steps along the margins of the river pebbles, is a Bombardier Beetle, Brachinus, one of approximately 500 species, distributed across tropical and subtropical riverbeds worldwide. It measures 15 millimeters. Its hardened forewings are a deep, non-reflective midnight blue. Its head and thorax are amber orange. Its antennae sweep the boundary layer of air continuously, reading the chemical signatures of the ground. It is, externally, an unremarkable insect. Internally, it contains a working pulse jet engine. To understand what the Bombardier Beetle is carrying, you need to descend past the external armor and into the microscopic anatomy of its posterior abdomen. There, completely isolated from the beetle's metabolic organs, sits a dual reservoir storage system, 2 symmetrical pairs of glands, each engineered to hold 2 highly reactive chemical substrates in long-term stable containment. The first structure is the storage reservoir, a large, elastic-walled gland lined with a thick, impermeable layer of specialized cuticle reinforced with cross-linked protein matrices. This lining prevents any chemical leaching into the surrounding hemolymph, the insect's equivalent of blood. Inside the reservoir sits an aqueous solution of 2 compounds, hydroquinone at approximately 25% concentration and hydrogen peroxide at 10%. Under ordinary conditions, this mixture is completely inert. The hydroquinone and hydrogen peroxide molecules drift past one another in the solvent without reacting, because the critical ingredient, a catalyst, is absent. No catalyst, no reaction. The system requires 0 energy to maintain this stability. It simply rests, a pool of dormant chemical potential, held behind a sealed gate. That gate is a sphincter muscle, a ring of dense circular muscle fibers that remains under passive tension, keeping the exit channel of the reservoir permanently closed. The tissue immediately preceding the valve is lined with mucus-secreting cells that add a secondary chemical seal. Not a single molecule of the mixture can migrate downstream, until the beetle's nervous system issues a specific command. Directly downstream from the storage reservoir sits the second structure, the reaction chamber. Where the reservoir is soft, elastic, and designed for passive containment, the reaction chamber is a rigid, heavily reinforced sphere. Its walls are thickened with multiple layers of sclerotized chitin that has been hardened through a biochemical process called sclerotization, in which phenolic compounds are introduced into the protein-chitin matrix, forming strong covalent crosslinks that produce a material with an exceptional strength-to-weight ratio and high thermal stability. The chamber is engineered specifically to contain explosive chemical stress and temperature spikes approaching 100 degrees Celsius. The inner surface of this combustion sphere is lined with thousands of microscopic exocrine glands that have secreted two catalytic enzymes, catalase and peroxidase, and anchored them permanently to the chamber wall. These enzymes are not floating freely in solution. They are covalently tethered to specialized cuticular filaments extending from the wall surface, forming a stationary, high-density catalytic carpet. They sit there, fixed and ready, waiting for the chemical mixture to arrive. When the beetle detects a direct physical threat, the pressure of a predator's jaw, the disruption of a shifting pebble, its central nervous system fires a signal down the abdominal nerve cord. The sphincter muscle of the storage reservoir instantly relaxes. The elastic walls of the reservoir execute a coordinated contraction. The mixture of hydroquinone and hydrogen peroxide is forced through the open valve as an atomized, turbulent jet into the reaction chamber. The moment the fluid contacts the anchored enzyme carpet, the reaction ignites. Catalase attacks the hydrogen peroxide molecules, cleaving their oxygen-oxygen bonds at the upper limits of enzyme kinetic efficiency, releasing free oxygen gas and water. Simultaneously, peroxidase uses the newly liberated oxygen to oxidize the hydroquinone, stripping away its hydrogen atoms to produce benzoquinone, a toxic, highly irritating compound. Both reactions are profoundly exothermic. The sudden rearrangement of molecular bonds releases a massive surge of thermal energy into the aqueous solvent. In a fraction of a millisecond, the temperature of the fluid jumps from the ambient 20 degrees Celsius to exactly 100, the boiling point of water at atmospheric pressure. The water in the solvent flash vaporizes into superheated steam. The liberated oxygen expands. The pressure inside the rigid reaction chamber spikes dramatically. The fluid has converted from a calm, liquid suspension into a pressurized, expanding gas-liquid matrix in less time than it takes a nerve impulse to cross a single synapse. What makes the Bombardier Beetle system extraordinary is not simply that it generates this explosion, it's how the explosion is managed. The Beetle does not release a single chaotic blast. It produces a high-frequency pulse jet, the same mechanical principle used in the propulsion systems of early aviation, operating at the scale of an insect's abdomen. Here is how the feedback loop works. As pressure peaks inside the reaction chamber, it forces open the terminal exit nozzle at the tip of the beetle's abdomen, expelling a jet of boiling benzoquinone and superheated steam into the external environment. That same pressure wave also pushes backward against the inlet valve leading from the storage reservoir, snapping it shut cutting off the chemical supply. With the inlet closed, the remaining fluid inside the chamber expels through the nozzle. The chamber empties. Internal pressure drops to near zero. With the backward pressure gone, the elastic walls of the storage reservoir push the inlet valve open again. A fresh charge of hydroquinone and hydrogen peroxide flows into the chamber. It contacts the enzyme carpet. The reaction reignites. Pressure peaks. Inlet valve snaps shut. Next pulse fires. This cycle repeats at up to 500 times per second. Each individual pulse is a discrete, perfectly timed packet of thermodynamic force, separated from the next by microseconds of complete structural rest. This architecture achieves two things simultaneously. First, it prevents the temperature inside the chamber from accumulating past the thermal tolerance of the chitinous walls. The brief gaps between pulses allow the tissue to dissipate heat before the next charge arrives. Second, it maintains a continuous, high-velocity stream that hits a target with the sustained impact of a jackhammer rather than a single blow. The enzyme catalysts, catalase and peroxidase, survive this process intact. Because they are anchored to the chamber wall, they are not swept out with the expelled fluid. They remain in place, reset automatically by the empty chamber phase, ready for the next incoming charge. The Beetle never needs to resynthesize them after a defensive event. The catalytic machinery is permanently installed. Specialized chaperone proteins embedded in the cuticular carpet prevent the enzymes from denaturing under the thermal spikes. Standard biological enzymes lose structural integrity and cease functioning at 100 degrees Celsius. The protective matrix within the reaction chamber preserves their folded active geometry across consecutive rapid-fire cycles, a level of thermal enzyme stability that exceeds anything achievable in standard laboratory conditions. The exit nozzle at the tip of the Beetle's abdomen is not a fixed aperture. It consists of two flexible, articulating sclerites controlled by asymmetrical muscle pairs. These muscles can rotate the exit opening through an arc of nearly 270 degrees, forward over the Beetle's own back, sideways through the gaps between its leg segments, or directly downward into the substrate. The Beetle can aim its defensive jet at a threat from almost any direction without altering its grip on the ground. This targeting capability is controlled by a network of mechanoreceptors distributed across the elytra and abdominal margins, microscopic hair-like sensors that detect the angle and magnitude of pressure from an attacking predator. The sensory data is processed not in the central brain, but in the local abdominal ganglia, bypassing the slower central nervous pathways entirely. The aiming response is a decentralized reflex, executing at the speed of a local nerve loop. The recoil of 500 steam pulses per second presents a mechanical problem. For an insect weighing a fraction of a gram, that backward thrust would easily dislodge its footing. The solution is in the Beetle's feet. The tarsi, the terminal leg segments, carry thousands of microscopic, bifurcated adhesive setae that utilize van der Waals forces to establish a temporary high-strength bond with smooth quartz surfaces. The Beetle anchors itself against the reactive force of its own internal propulsion, remaining stationary through the entire defensive event. The thermal management of the surrounding tissue is handled by an arrangement of low-conductivity air sacs surrounding the combustion zone. These empty spaces act as a natural thermal barrier, preventing the heat of the 100-degree reaction from conducting inward toward the beetle's reproductive and digestive organs. The thermal energy is directed exclusively outward through the nozzle. The internal core remains at ambient temperature throughout the event. A predatory beetle, tracking movement along the riverbed, closes on the bombardier and clamps its mandibles against the elytra. The response is immediate. From the human observer's perspective, holding a low-intensity torch a meter away, the event is a single sharp audible pop and a flash of white vapor. The pop is the acoustic signature of high-pressure steam breaking the local sound barrier at the nozzle tip. The vapor is a perfectly directed linear jet of boiling benzoquinone and superheated steam, targeted with geometric accuracy at the predator's head. The predatory beetle is hit with fluid at 100 degrees Celsius, coated in benzoquinone, a compound that is both a potent skin irritant and a chemical signal overwhelming enough to saturate its chemoreceptors. It recoils immediately and retreats into the gravel. The Bombardier Beetle does not pursue. The moment the external pressure on its elytra ceases, the feedback loop stops. The inlet valve drops back into passive closed position under sphincter tension. Steam production halts. The temperature inside the reaction chamber begins its smooth descent, heat dissipating into the thermal sink of the surrounding environment. Within milliseconds, the only evidence of the event is a faint wisp of white vapor rising toward the acacia canopy, and then nothing. The riverbed returns to its prior silence, completely undisturbed. The Bombardier beetle's lineage belongs to the carabid beetles, one of the oldest and most species-rich families of terrestrial arthropods, with a fossil record extending back over 200 million years. The chemical defense system itself is ancient. Simpler versions appear in related beetle genera that produce benzoquinone secretions without the pressurized pulse jet, suggesting an evolutionary pathway in which the reservoir chemistry evolved first, and the pressurized feedback mechanism was refined afterward, over geological time. What the fossil record reveals is a consistent pattern. The carabid lineage survived major extinction events, not through scale or speed, but through chemical ingenuity and microhabitat specificity. By colonizing the complex, buffered microenvironments of riverbanks, leaf litter, and soil, habitats insulated from the thermal and atmospheric volatility of the surface world, these beetles placed themselves in environments where the dominant survival challenges were predation and chemical defense rather than temperature extremes or resource depletion. The riverbed environment itself is ancient and stable by geological standards. These seasonal channels have filled with water during monsoon rains and receded into dry phases for millions of years, maintaining a consistent physical character that the beetle's biology has co-evolved with across deep time. The alluvial sand and fractured clay are not just a backdrop, they are the thermal sink that absorbs the heat of the beetle's defense, the substrate that the adhesive setae grip against recoil, the labyrinth of microtunnels that provide shelter between events. The beetle is not adapted to its environment. It is built from it. Every molecule of hydroquinone and hydrogen peroxide stored in the reservoir required metabolic investment to synthesize sugars, amino acids, enzyme precursors. In the resource-constrained environment of the savanna, where food is seasonal and competition is constant, this represents a significant biological expenditure. The design of the system reflects the pressure to conserve that investment. The enzymes are anchored permanently and never consumed. The reaction chamber self-resets between pulses. The nozzle targeting minimizes wasted spray. The air sacs protect vital organs without adding metabolic mass. The setae anchor the beetle against recoil without requiring active muscular effort. Every component of the system serves multiple functions simultaneously, and none of it requires conscious management from the beetle. The chemistry is automated by physics. The targeting is automated by local ganglia. The pressure regulation is automated by the mechanical geometry of the valves. The beetle does not operate its defense. It simply relaxes the sphincter, and the system runs its own feedback loop to completion. This is the principle the riverbed teaches at 2 in the morning. Sclerotized chitin, enzyme carpets, fluid pressure differentials, van der Waals adhesion. Taken individually, each is a simple physical phenomenon. Assembled into a beetle, they produce a system that has operated continuously and reliably for over 200 million years, in environments ranging from tropical riverbeds to temperate forest floors requiring no external energy input, no conscious management, and no maintenance beyond the beetle's own metabolic housekeeping. The riverbed is quiet again. The Bombardier Beetle has resumed its slow patrol along the pebble margins, antennae reading the chemical signatures of the ground, sphincter valve closed under passive tension, reaction chamber cooled and reset, enzyme carpet waiting. The quartz gravel is still radiating the last of the day's heat into the cooling air. The acacia canopy is motionless. The stars are indifferent. There is nothing left to manage tonight. The systems that matter are already running on their own. The slow thermal exchange of the earth, the chemistry waiting behind closed valves, the ancient self-resetting machinery of a living world that has been doing this since long before anything had a name for it. Let your body follow the riverbed's lead. The heat of the day is dissipating. The ground is cooling. The feedback loops are at rest. Good night.